Redox 3, the third in the series of redox topics, and this one will focus on electrolysis. So let's get started. First, you need to understand how we can check to see if something conducts electricity. And I've drawn a very simple diagram. Power pack, leads, bulb, or an ammeter connected to that material there, whatever that material might be. And if you understood the topic on bonding and structure, you should then be able to explain why certain chemicals conduct and why they don't conduct. Let me show you this apparatus. So we have a power pack plugged in. There's a bulb, and just to test the equipment, I can connect these two crocodile clips with each other like that, and the bulb lights up. So the bulb lighting up will show that we've got electricity flowing, and we could put a meter. We could put a meter in instead of the bulb, but I hope the bulb will serve for our purposes instead of a meter recording a current flowing. Now, because there's a current flowing there, that shows us that there is a flow of electrons around the circuit. Electrons are flowing around the circuit. That is electricity, and that is that is electrical current. Right, let's put some chemicals in here, and you should know how and why they conduct electricity. Well, first let's pick a metal, and it just seems a bit tiny, this, but I've got a tiny piece of copper. And copper is a great conductor. If I connect one side and the other side up, there is a gap between them. The bulb comes on. Look, the bulb is on. Maybe move everything back a bit. You see, the bulb is on, showing you that metals conduct electricity. Now, a bigger metal would be my keys. Look, if I clip onto my keys there, clip onto the key there, you can see the bulb comes on, showing you clearly that metals conduct electricity. And why is that? Well, that's because of free electrons. These metals have, all metals in fact, have free electrons. And by free, I mean freely moving around within the structure. So in this piece of metal, lots of electrons are moving around. In my key, lots of electrons are moving around freely. And those free electrons cause the conduction to happen in such an apparatus. Well, what about other chemicals? Well, metals conduct. How about ionic things? Well, here I've got sodium chloride, and if I get a beaker and put solid sodium chloride into a beaker and then use one of these pieces of equipment. These are graphite rods which I can put into the apparatus like that, and I can clip the crocodile clips onto those and see if solid sodium chloride conducts electricity. And look, it does not. Solid ionic things do not conduct electricity. I can get an even block, a block of something ionic. I don't know what this is. I think it's potassium aluminium sulfate, alum. But I can put these paper clips on either side, and again, you'll see no light coming on, and therefore these do not conduct electricity. Solid ionics do not conduct electricity. Why? Well, they don't have free electrons and they don't have free ions. So Solid ionics do not conduct electricity, and I will show you an experiment later where a liquid ionic, if we could melt that, if we could make this melted sodium chloride, if it was melted sodium chloride, it would conduct electricity, because then the ions would be free to move about. But what about a simpler way to free up the ions? What if I take the sodium chloride and dissolve it in water? Well, that's sodium chloride solution. Put that in there. And now, if I put that apparatus in there and connect these up, see, the bulb comes on. The bulb is on now. It's flickering a bit because of the quality of the bulb, probably. I've bumped up the voltage a bit, and now it's not flickering. That is on. It's on because the ions are free to move about, and the moving about free ions will conduct the electricity for us. Ionic solutions conduct. Ionic liquids conduct. Ionic solids do not conduct. You need to know the reasons why. Excuse me. And I will cover the reasons again in my PowerPoint once I've got this demonstration out of the way. Well, what about covalent things? Now, if I had a candle, I could connect these to a candle like candle wax, and they wouldn't conduct. So solid covalent things do not conduct. How about liquid covalent things? Well, this is like an alkane. It's called low toxane. It's a safe alkane. And if I just get one of these again and clip onto the electrodes, we find that the bulb there, the bulb does not come on. Low toxane does not conduct electricity. Typical of covalent compounds. Covalent compounds do not conduct electricity, whether they're solids like wax, whether they're liquids like low toxane, whether they're gases like oxygen. Solids, liquids, gases do not conduct electricity. There is only one eventuality where they do conduct electricity, and that is in things like hydrochloric acid. Now, you should know by now what causes an acid to be acidic. Hydrogen ions. We make this by taking hydrogen chloride gas, dissolving it in water. So this is a solution. So if we start with a gas that's covalent, hydrogen chloride, the gas won't conduct electricity. But if we put it in water, dissolve it in water, that's HClAq, hydrochloric acid there, same apparatus, the bulb comes on. See that? Bulb comes on because that hydrochloric acid has got hydrogen ions and chloride ions. Remember the definition of a strong acid? It's an acid that when dissolved in water turns into ions fully. So I've got lots of hydrogen ions, chloride ions freely moving about. And when I've got freely moving about ions, then it will conduct electricity. Okay, let's switch you around to my PowerPoint. So carrying on with the PowerPoint, that was the apparatus set up. In exams, these might be drawn as straight lines. You're familiar with that. You should be familiar with that from physics, where we draw circuit diagrams using straight lines to represent leads. I've just drawn them zigzaggy because I think they look more like leads. So let's get to grips with why things conduct electricity. Now this is crucial. There are only two reasons why anything, anywhere, ever conducts electricity. Reason number one, it may contain freely moving electrons. Anything with freely moving electrons will conduct electricity. Reason number two is it will contain freely moving ions. They are the only two reasons why anything conducts electricity. So what if you don't have reason one or reason number two? Well, then it will never ever conduct electricity. So if a chemical has no free ions and there's no free electrons, then it will not conduct electricity. But if it has one of those two ideas, either, then it will conduct electricity. So let's have a look. This is what my demonstration earlier was designed to do. Metals conduct, yes. Why? Because they have free electrons. Now, if you don't understand them having free electrons, you need to go back to the bonding topic and look at metallic bonding. Metallic bonding, metals, they have positive ions with freely moving electrons around them. The freely moving electrons cause the conduction. Well, how about ionic solid? No, there's no free ions, no free electrons. Ionic liquid? Yes, because the ions will then be free and they will conduct electricity, and that's my first electrolysis experiment I'm going to show you later. Ionic gas. It's not easy to get an ionic gas. You've got to take an ionic solid and boil it, and that's not easy to do, so I haven't been able to do that. But if you could do it, then because the ions would be free, it would conduct electricity. I did show you sodium chloride solution. I did show you salt solution, and the salt solution did conduct. Why? Because the ions are free. How about covalent solids, liquids and gases? Covalent things do not conduct electricity because all the electrons are in energy levels, they're not freely moving, and covalent things are not made of ions. So there's no free ions, no free electrons, does not conduct electricity. And finally, things like hydrochloric acid. They're covalent solutions. So some do, and those the ones that do contain free ions that are freed up by dissolving the covalent substance in water or some other solvent. No, normally the solvent is nearly always, 99% of the time at GCSE, the solvent is water. So let's recap a few fundamental ideas. Electricity is a flow of electrons. That's a physics idea. We assume you know that in chemistry. When metals conduct, they may get warm because of electric current flowing through them. When electric current flows through wires, they often get warm and hot. Sometimes they can get dangerously hot and catch fire. Depends how much current is going through. But when they go through and the metal is nice and thick, then they might get warm, but the metal does not fundamentally change. The metal that you've got is not turning into anything different. So that's just normal conduction. Now, this is slightly different. This is electrolysis. Some chemicals, they will conduct electricity, like sodium chloride solution, like hydrochloric acid. They'll conduct electricity and they will make some new chemicals when they do so. And when they will be decomposed, making new chemicals, those chemicals we start with that conduct and decompose, making new chemicals, we say they are electrolytes. So the definition of an electrolyte is something that will conduct electricity, and as it does so, that electricity will decompose it, making some new chemicals you did not have before. That's an electrolyte. And the process going on when you pass electricity through electrolytes is known as electrolysis. So electrolyte definition, electrolysis is the process by which we decompose chemicals by passing electricity through them. First experiment. There are about 4 or 5 experiments within this section that you need to know about. And this is probably the most famous one of all. Say, I've taken a very simple diagram here off the internet. Say you've got lead bromide in there, lead bromide. Lead bromide is ionic. Lead bromide, when it's a solid, does not conduct. What if we melt it? Well, if we melt it, it'll be liquid. Then the ions are free. Then it will conduct. And when it conducts, you get a reaction where you get lead at the negative and you get bromine at the positive. The overall equation for the electrolysis is lead bromide breaks down to make lead and bromine gas. Now, when I demonstrate this, the lead being formed is relatively safe, it's formed in there, but the bromine being made is dangerous. The bromine is, you've got to be really careful of it. And you've got to do this in a fume cupboard. The fume cupboard will take the bromine bubbles away out of harm's way and not give you any chance to breathe in bromine. Now, breathing in bromine is very dangerous and not to be advised. Just wanted to point out that the negative electrode is actually called the cathode and the positive electrode is called the anode. You know which is the negative electrode, the cathode, when it's connected to the negative of a power pack. I'll show you in a minute. The anode, equally, you'll know when it's the anode because it's connected to the positive side of a power pack. Right, let's show you the apparatus. So this is the apparatus. We've got the negative here. This is the cathode. So that's on that side of the apparatus. This positive is going through a bulb and then connected here. So that's the anode. So cathode, anode. And this is lead bromide. Lead bromide, solid. Now if I turn the electricity on, can you see? The bulb is not lit. When the bulb's not lit, it shows you there's no conduction of electricity. And you should know the reason for that is the ions are not free to move about. Well, how can we get the ions there moving about? See, it's solid. Solid, the ions are in their places, they're vibrating, but they're not moving around. We need to get them moving around, and therefore, maybe we melt it. Now, when doing this, you have to be careful not to melt the leads as the heat is being supplied. But if we wait a while, probably about 5 minutes, then lead bromide will melt. When it melts, the ions will be free to move about. And when they're free to move about, we'll get electrolysis. Electrolysis whereby this chemical, lead bromide, will turn into lead and bromine. The electricity will break down the compound into lead and bromine. And when that happens, that's electrolysis. And this chemical that breaks down is then known as the electrolyte. So as I say, it will take a bit of time to get going. And maybe I can do something else in the meantime. Let me just pause it. So here is the apparatus. What I want you to think about is that cathode there is negative. At the negative, lead ions. If they can be free to be moving about, then the lead ions will go to the negative. And at the negative, they will pick up 2 electrons. Look, lead ions pick up 2 electrons, and when they pick up 2 electrons, they turn into lead. So if we go back to the apparatus, I want to look at the cathode, the negative electrode. I want to look to see if there's lead made. Now that'll be hard to see. From my experience, that's hard to see because you've got this grey lead bromide solid going on in there, and we won't see a lump of lead, although it will be there. We won't see it very well. However, on the other side, we will see that, because on the other side here, bromide ions are negatively charged. Those negative ions will move to the positive electrode, the anode, and they'll turn into bromine and they'll give off electrons. So giving off electrons, oil, is oxidation. Taking in electrons is reduction. So that's what we're hoping to see, and I'm hoping to show you bromine being made. It's a brown gas, and we'll see it as bubbles. Let's take you back to the apparatus. So, back to the apparatus. You can see here that the bulb is not on. Bulb's not on yet. The mixture is starting to melt. It will take a bit of time. And then we've got this whole thing going on. This whole thing going on inside a fume cupboard. Now the fume cupboard is needed to carry away any dangerous fumes of bromine that happen. I think if I take the phone off the stand, or my camera on my phone, off the stand and show you, I'm hoping you can see the bromine gas being made at the anode, the positive. So let's just think where that is. Positive, this one, through the bulb. Only when the bulb lights up will we know that electricity is flowing. And only if the electricity is flowing will we get bubbles of bromine gas here. On this side, we get the lead at that electrode. There, the bulb's coming on. Can you see? The bulb is coming on. I'm going to just take this off the stand. There, the bulb is on. Can you see the bubbles on the left? The bubbles on the left. Maybe you can see them there as well. The bubbles on the left are bubbles of bromine gas. Now we need to turn the fume cupboard on. If I bring this down, I can talk to you about it a bit more. There, the bulb is on. The lead bromide there is liquid. It's liquid. The ions are, positive ones are going to the negative ions are going to the positive, and they're being discharged. Now this is the heat. So I take the heat away. Then that beaker there will cool. The lead bromide there will cool down. As the lead bromide cools down, it's going to solidify. When it solidifies, the bulb will go out. It's what we started with. With solid, the bulb and conduction of electricity will not happen. So I hope you saw the bubbles here, and I hope you trust me when I say lead is made on the other side. And because it will take a bit of time for that to cool down, then maybe I can do something else. But I quite like my classes, seeing the bulb get dimmer and dimmer and dimmer before it finally goes out. So maybe I will just leave it there for a while. Or maybe I can be naughty and get I've got a squeezy bottle, and you shouldn't do this. You shouldn't do this because the glass will crack. But just to speed it along a bit, now, cooling it down rather spectacularly quickly like that. Can you see the bulb's now gone out? Bulb's got out because that's solid. Solid lead bromide. So that's not the standard way to cool it down. The standard way to cool it down is to let it cool down and be patient. Right. So let's take you back to my PowerPoint. So back to PowerPoint, the summary: lead bromide turning into lead and bromine. Lead at the cathode, bromine at the anode, the bubbles that you saw, etc.